Hello, my name's Rich Edelman from Siemens EDA, and I'm here to talk to you about DPI today, specifically about making your DPI-C interface a fast river of data. So what is DPI-C really? Well, it's about the bytes, moving the bytes. We have some SystemVerilog on the left here in green, and on the right, some C code in orange. That's how it's going to work in this talk. SystemVerilog code is green, C code is orange. And we have some bytes over on the SystemVerilog side. There are these blue things, and they're going to get sent over to C by calling a function. And then they're furthermore going to get sent back over to SystemVerilog, some other call. And those bytes will get processed and things will happen to them. And so what is DPI-C really? Well, it's a C callable interface to pass bytes between C and SystemVerilog. Well, what's a C callable interface? A C callable interface is just how C calls itself. So it's a stack pointer and you put data on the stack and then jump. So a function can have arguments, it can have a return value. And in this case, we have a function G calling F, and we're going to jump. It's going to print and return. And this is the disassembled machine code from a Intel processor. And it's putting things on the stack and then calling F. And then inside F, we're getting things off the stack, putting them on the stack, and calling print. So it's just C. So what's going to happen with DPI-C is SystemVerilog and C, they're going to work like C function calls. What else is in DPI-C besides moving the bytes and the C callable interface? Well, in DPI-C, we call C code its imported calls, meaning I'm importing calls from C into SystemVerilog. I can call those from SystemVerilog and it'll execute the C code. Or I have SystemVerilog code, which I'm exporting. So now C code can call that. Those are called exported calls. So we have imported calls and exported calls. Really, that's just vocabulary. What about functions and tasks? We can call either one of those. So in SystemVerilog, there's a differentiation between a function and a task, which is timing. So in a task, timing is allowed. In a function, there's no timing. What else is in DPI-C? There's some include files that are built in that have various things in them, including access routines. And then it's very nice if you have helper files like a DPI header.h that gets generated when you compile your SystemVerilog. So you write your SystemVerilog code and you use a switch like this, and it creates a file which defines the C callable interface that the C compiler should expect. Then in your C code, you can include that file, and now the interfaces will agree because the compiler will check them. And if they don't agree, you'll get a message. And this way, it's a lot easier to debug. So what's the simplest DPI-C code I could think of? We have a module here, and we declare the import function and the export function. And here is the exported SystemVerilog code. It doesn't do anything except print. And then all we're going to do in the initial block is we're going to call the C code, pass an argument over. We jump over into C code, we print it out, and then we're going to call our SystemVerilog code, incrementing the argument, call the SystemVerilog code, and print it out. And the thing that's going to come out in our DPI header.h is the definition of those C functions that we can use. What data can we pass back and forth in DPI? Well, these are the arguments that you can pass. You can check the LRM. They're the usual arguments. So char, which is a byte, short int, long int, short real, that's a float, double, void star, strings, logic is passed as an unsigned byte or unsigned char, bit, same thing, unsigned char. What about the return values? They need to be those same things, the small built-in types. What about tasks? Well, so we already talked about functions and tasks. So the difference between them is A function cannot consume time, and it can have a return value. A task can consume time, but no return value. And in this talk, I'll just talk about functions really, but you can call a task anywhere. There's a few extra pieces of syntax you may need. So what about tasks and C? Imagine in SystemVerilog, you have a fork join none, and there's 3 legs, and you're going to call some C code. So now you're over in C, and the C might call some SystemVerilog code. Now we're over in SystemVerilog, and we hit an @POSEDGE clock. Well, that's going to cause the simulator to yield. It's going to suspend, and some other thread's going to run. For instance, this next thread. I'm going to call my C. It's going to call over into SystemVerilog again and maybe hit POSEDGE clock, and same thing. So these 3 threads now are all running in parallel, and there can be some interesting things happen in your test bench because of that. So that's the reason to use tasks. So passing data, how do we move those bytes? So we can move bytes by copying them. So we copy them from point A to point B. We can point at them. So when we point at them, that's like passing by reference. And in general, we want to not copy, we want to point. But you can't always do that. There's some data that may be optimized for the simulator, but in order to give it to C in a C layout, a C-friendly layout, we may have to copy it or move data around. So we want to pass data in on inputs, of course, and pass data on outputs. That's out. And inouts in SystemVerilog are both in and out. Keep that in mind. We'll visit that again later. Now, here's a quiz. If you have an array of 1,000,000 bytes, which is faster, copying the 1,000,000 bytes or passing a pointer to the 1,000,000 bytes? So that's what we're going to try to remember about references and avoiding copying. So let's get into some code. Here is 2 states, so that's a bit. So we have a C function that has some bit arguments. There's input, output, and inout. The examples we're going to show here and in the paper are very simple examples, and they're generally all structured like this. There's a C function and a SystemVerilog function, and they all take an input, an output, and an inout argument. And they don't do anything useful except demonstrate that we can make those calls. So in this case, we're going to hit our initial block, call the C code, jump over to C, and increment things and do things, maybe call back into SystemVerilog and return. Now in this case, we see that the input is just an SV bit, and the output is a pointer to an SV bit. Now, if you remember your C programming, an output from a function, that means I need to pass it back, and so I'm going to need a pointer to that argument so that I can put the value somewhere in the caller. And for SystemVerilog, of course, we don't need that. We don't have pointers. It manages all that on its own. So we'll pass in O. That's the space where we would like to have the output land. And when we want to set the value in C, we'll do *O. So the SV bit is defined in our built-in file svdpi as an SV scalar, which is further defined as an 8-bit quantity. So that's a C compiler. That's a built-in type 8-bit quantity. So a bit is represented by 8 bits. We have 4 states. It's the exact same code. Over it goes. This time it's SV logic, and an SV logic is defined as an SV scalar. It's the same as it's an 8-bit quantity, and there's a built-in representation that you can use. These defines for 0, 1, 2, and 3. So an SV logic is a 4-state. It could be 0 or 1, Z, or X. The previous slide was a bit. That's a 0 or a 1. What about arrays of C native types? So how about an array of integers? So we create a little type def here, A of I. That's an array of integers. And then we're passing that around. And there's 10 of them. It's a fixed size array. So we can use for each to go through them and increment and point and things. We call a function in C and jump over. And the argument is a pointer to an integer. And even for the output, inout's pointer to integer. So we can just use a very easy programming style, a syntax, to just say I sub x, O sub x, IO sub x. We can call our SystemVerilog with those arguments, get the answer back, and return. So arrays of native types, arrays of integers is very easy with DPI. What about a bit vector? So this is an 8-bit vector, and we have our functions using that type, bit vector underscore t. And we initialize, call over, and that is a pointer to an SV bit vec val. Well, what's an SV bit vec val? That is a 32-bit value. It's a 32-bit quantity from our SV DPI. So that means we're getting a pointer to a 32-bit value. And now it's an 8-bit value, so I can just I can increment, I can set the value just like I was treating an integer. I just have to remember that only those low 8 bits are going to get used. What about a 4-state bit vector? So here's a 4-state bit vector. Same code, we initialize, call over to C, and we get SV logic vec val pointers. What's a SV logic vec val? Well, that starts to get interesting now. It's a struct. So it's a struct of two 32-bit integers, A val and B val. And if you're a PLI person, that should sound familiar. So we get a pointer to a struct over here. So O has a val and it has a B val, and we can set them however we want. So in this case, we're copying the A val of I into O, and we're just setting the B val. So now we have on the C side just a struct and pointer access. Pretty easy code to write. What about passing actual structs? So in this case, we have a struct that we've written on the SystemVerilog side here, typedef struct, and it has a B, an L, an I, and a long int in it. And when we generate our DPI header, this is generated code. It generates exactly what the struct is. And we can see a bit is an SV bit, a logic is an SV logic, and so forth. As we get over to our C code, we actually get a pointer to that struct. So we have that struct over in C that we can reference and use. So we can reference the B and the L and the I and the LI. What if we had arrays of structs? Well, really, it's the same code, but it's a really big struct. So in this case, on SystemVerilog, we wrote this really big struct with a bunch of different kind of types. So here's bits and regs, a byte, short int, long int. And this is what you get in your DPI header. So these things are defined in the SystemVerilog DPI as SV packed data n-elms. And it's telling you how to do the math on that so that it makes a big enough array over on the C side. And then it's these types that we just talked about, SV logic vec val or SV bit vec val. Yeah, DPI header.h is pretty interesting. What about besides passing data or bytes, what about setting and getting the scope? So here we have a top and an instance, another module, an other module. And we call some C code, and we get into the C code, and there's a helper function built into DPI-C, and it's SV get scope. It gets the current scope. So we're going to get the current scope, and then we can ask what its name is. We get the name. And then we make a function call. Now that function call is to the scope we're in right now. So that call is to the scope we're in, which we haven't changed the scope. So it's our scope we came from. So that's going to come back to this function. Now, if we want to try some other scopes, we can get a scope from a name. So we give it a name, and it's going to give us back a scope. So we give the other module, set the scope to that other module, now call that same function call, but it's implemented over in this other module, fscope test SV. So that's a way to change the scope, change the context. Now, if we want to go back to the original calling scope, we can just do SV set scope scope. So we did an extra lookup on the name, but we didn't have to do that since we had that variable. Oh no, we overwrote it. Yeah. So this is a clean way to do it. Always look up from the name, and then you can get back. Now we're going to call this other SV scope test SV function back in the original. There's some special things in SystemVerilog called C handles. C handles are an opaque handle that you can't really do much with in the SystemVerilog side. What they are is they're C handles that you're passing around. You're just using SystemVerilog to manage them, maybe. So in this case, we've got a call to C handle underscore C, and over there, all we're doing is we're calling malloc of some object type, and we're going to return that handle P. So this is a case where the C code is creating an object. It's creating a variable location that we can manipulate or use later, an object, and it's returning that handle. And then later, we could pass that handle back into some other function as the handle of choice and do something with it. So C handles are very useful for managing objects and data structures over that have long lifetimes over on the C side. What about performance? So that quiz that we took before, we definitely want to pass by reference, and we want to not do copying, but we're still concerned about that code inside SystemVerilog. Well, my experience is it's the same performance as a C function call. There's nothing extra. There's a little bit of overhead for tasks, but it's quite minimal. And so, we want to be smart about how we program. Instead of calling a function 1,000 times, we would rather call a function one time and pass a large quantity of data in. So if you find you're writing DPI-C and you're making a lot of calls, well, that's just going to be slower than it might otherwise be. So minimize the number of calls. But the other thing that you can do is you can check with your vendor, and if you write your code a certain way, then what's going to happen is there will be no copying. And in this case, what we have is we have a type called big data, and it's 1,000 integers. And because we've written it as integers, and because it's going to be an import function, not an export, not an output, it's only inputs and inouts, array of integer, import function. And we're going to benefit, there's no copy in, there's no copy out of the data. Essentially, when we jump over to C, we are using the 1,000 integers in that array that are in the simulator. Now, we have to be careful to not write bad code and scribble all over memory, but that's a huge performance boost. It can be 2 to 5 times faster to not do that copy. So here's a case where we have this array of 1,000. We're calling over 10 million times, calling over to the C side. We have these handles, an input and an inout, and we're going to do some math on it. Now you might ask, well, wait a minute, how do I get answers back out of that call? Well, it's a little bit of a trick. Since it's an in-out, we can get answers back out. So we're going to use the in-out as a place to put the answers, as a place to get the output. Okay, for performance, what about a two-dimensional array? Well, the same thing. It's also optimized. So we have a two-dimensional array, and we initialize it, call over to C, and we're gonna type in that same definition over here because our DPI header.h is not going to give us this type. We'll just type that in, and then this is the API that is going to be DPI header.h. It's going to tell us that we have pointers to integers. Well, we don't want to do that because we want to write clean code. And by clean code, I mean we don't have to do pointer math. If you have to start doing a lot of pointer math, it gets scary. So in this case, we have the DPI header.h sort of version of the API. We're going to call a clean version. So we call the clean version, and now we can write code like, IO sub x sub y equals I, and so forth and so on, and do the math that we need to do. So in this case, because we've written it in the way that allows for no copying, and we have a clean way to write it, it makes the two-dimensional arrays very nice to use. All right, well, how about a couple use models? So we have all of this structure in place, and now we want to do something useful with it in DPI. So I have some C code. I have a model here that I'm running, and it's a fancy checker, or it has some fancy algorithm. And I synthesize time over here in this loop. I synthesize time by calling into SystemVerilog. I call tick-tock, and that goes over and waits for an event or waits for a certain amount of time. And so in my C code, I have a lot of math that's going on, a lot of algorithms, and I'm going to insert a little bit of code in there and record those values into the wave database. And I'm going to use set scope and get scope and things like that. And then I'm going to call a couple functions. So the couple of functions are record my struct and record an int. So I've built those, and record my struct and record an int. All they do is they assign their value that they got from their argument. They assign that value to a field in this interface. I built an interface, could have been a module. I built an interface called a recorder, and I put the type in there that I want to record. I want to record the struct, and I want to record an int. So I have two variables, s and an int. So as I run my C code and time is passing, I run my fancy algorithm, I can see in the wave window it's recording top.recorder_1.s and top.recorder_1.an_int. And so in my C code, I've instrumented it. I could hide some of this with macros or function calls. I have implemented it, so I'm going to go look for a scope, get the scope from the name. That I'm naming these variables. This instance of variables is going to go on that row in the wave window. So I set the scope, and then when I call my functions, I'm calling the functions that are in that instance. So that's a really quick, handy way to put C code in the wave window. There's a little bit of overhead for this instrumentation, but if you have a big checker or a big algorithm and you want to put some variables in, it's actually really easy to do. Okay, another use model is using some of the helper functions that are inside the DPI. Well, so there's actually a lot of helper functions in there. Some of them are quite scary, so I generally avoid them. But there are some that are quite useful. And there's a thing called open arrays. Open arrays are dynamic arrays. So in this case, I have a two-dimensional dynamic array. And in the SystemVerilog side, I'm building one dimension, then I'm going through and building the second dimension. So it gets all built out. It's a random size array. And then we're just going to call a C function with those array handles. So it's an array that got built dynamically, and you call over to C. Now on the C side, it's a special handle called an SV open array handle. And it's really a void star, but it's an SV open array handle. And if we want to get at the items that are in there, we want to go use this SV get array pointer. That's going to help us find the data. SV get array pointer, SV get array pointer. So now we have the three pieces of data. We can ask the handle I, we can ask it, what is the first dimension size of U? And then what is the second dimension size of U? And we can get the dimensions. We can set up our little array to go through them and process them, and do a bunch of things with those handles, incrementing the pointers through the arrays. Now it's starting to get a little hairy, and maybe this is as far as I would take it. And we're going to go get the place, the O, and we're going to go get a place which is index 2 sub 3 and set the value to 23 by doing math. So you can check my math. I'm pretty sure that's right. And that's going to set the value in the memory. And then, of course, we'll return that's an output. Well, thank you very much. I hope you agree with me. DPI-C is an easy and powerful way to combine SystemVerilog and C for a variety of things like modeling and checking, verification. Overall, just keep it simple. Try to not copy large amounts of data. And the things that SystemVerilog is good at, leave them in SystemVerilog, like 4-state and bit vectors and things like that. Thank you very much.